Dennis Hyde, welcome to our webinar. I'm the marketing manager for oil and gas applications with Veolia Water Technologies. I'll be your moderator for today's webinar, High Recovery Membrane Technologies for the Oil and Gas Industry. This webinar is going to focus on a few technologies designed for high fouling and scaling applications, such as the treatment of produced water, cooling tower blowdown, and refinery wastewater with a membrane treatment approach that achieves high water recovery and stringent water quality requirements. This webinar will review an upstream and a downstream oil and gas case study. And if you want more information, you can print out or save our handouts that are going to be on the right side of your screen. We have a handout on one of our technologies, OPUS II, and that'll give you more specifications if you're interested. John, can you advance the slide? So before we start the presentation, here are a few housekeeping notes. You should be hearing me speak right now. There are two options for audio. You can listen either via your computer or you can call in with the call-in number in the confirmation email that you should have received an hour ago with webinar instructions. Also, on the right hand of your screen, there's a questions panel. Feel free to enter questions there. Everyone is already muted, so we won't hear you speak, but you can type in questions here, and only myself can see those questions, so don't feel like you're broadcasting the questions to the group or anything like that. After the webinar, you'll be directed to take a 3-question survey. It'll just take you a minute. Please take it and give us feedback on today's presentation. You can also give us ideas for future webinars on water or wastewater topics. So your feedback does matter. Okay, next slide. So let me introduce our presenter today. John Corpiel is a principal engineer with Veolia Water Technologies. He has 23 years of experience in industrial water and wastewater treatment. 17 of those years are here with Veolia. John specializes in the process design, optimization, and troubleshooting of physical and chemical treatment systems, including integrated membrane systems. His focus is on water and wastewater treatment applications in the oil and gas, mining, and power industries. He is a co-inventor of a Veolia patented technology for produced water treatment, and he holds a bachelor's and a master's degree in civil and environmental engineering from the University of Pittsburgh, and is a licensed professional engineer in Pennsylvania and several other states. So it's great to have John on with us today. Thank you, John, for presenting. The floor is now yours.
Well, thank you, Dennis, for that nice introduction. So as indicated by the title of this webinar, I'm going to discuss high recovery membrane technologies that are used in the oil and gas industry. Before I review the agenda, however, I just want to briefly define recovery and its importance in oil and gas industry applications. So as most of you know, the term recovery or water recovery is defined as the ratio of the quantity of treated water produced by a treatment system to the quantity of feed water used. For some applications, achieving high recovery is important to maximize the amount of treated water that's available for reuse, especially in locations where water is scarce. In other applications, however, achieving high recovery is important to minimize the amount of liquid waste that needs to be disposed of, especially when brine disposal options are limited and the cost of trucking away liquid waste for offsite disposal is expensive. So as indicated in the agenda here, I'm going to give you an overview of Veolia's ROS technology and briefly share a case study of that technology utilized in an oil field in Utah. Then I'm going to give you an overview of Veolia's second generation OPUS technology and share 2 case studies, one for reuse and surface discharge at an oil field in California, and another for a boiler feedwater application at a refinery in the Midwest US. So first I'll give you an overview of ROS technology. ROS is an acronym. It stands for removal of oil and grease, solids such as particulates and bacteria, and scale formers like hardness, silica, iron, and barium. These contaminants can cause fouling and scaling issues in oil-filled injection wells, in the piping for frac water or injection water supply, and plug the pores of an oil reservoir, reducing its oil recovery and increasing operating expenses. So before I get into the details of ROS, I want to first give you some context of applications where it adds value. ROS is used in reuse applications for oil exploration and production operations. These are some examples of where it can be used. Treating shale oil production produced water and flowback water for reuse as frac water. Treating water flooding produced water for reuse as injection water when it's used in conjunction with a downstream deaeration gas stripper, as we'll show you in a case study. And treating steam flooding produced water for reuse as a steam generator feed water when it's used in conjunction with downstream ion exchange softening, as we'll show you in yet another study. So applying ROS in these reuse applications allows the oil field to become less reliant on consuming freshwater sources and allows them to minimize their liquid waste that would otherwise need to be disposed of. So the ROS process is a combination of two technologies. It combines Veolia's proprietary multi-flow high-rate chemical softening process with ceramic ultrafiltration membrane technology, and it achieves a high recovery of high-quality water that's suitable for reuse in steam flooding, water flooding, and fracking operations. So the feed water, which is produced water from an oil field, is first treated with Veolia's high-rate chemical softening and thickening technology called multi-flow, which removes scale formers, and also TSS. And then alkali chemicals such as lime or caustic are added to the precipitation tank to raise the pH to soften the water, precipitating hardness in the form of dense solid precipitates. Silica removal, if it's desired, can also be accomplished by the addition of a magnesium salt to facilitate the co-precipitation and absorption of silica onto the chemical softening solids. And the dense solids that are generated by the multi-flow softening process are removed in the settling zone of the multi-flow using lamella plates. A portion of these solids are recycled to the precipitation tank to provide seed for crystal growth, and then excess solids are intermittently purged from the multi-flow and are sent to a filter press for dewatering. The dewatered sludge cake is taken to a landfill for disposal. The multi-flow effluent is then processed through ceramic ultrafiltration technology. It's operated in cross-flow mode, and the membranes can remove free oil, suspended solids, and bacteria to very low concentrations in a single step. The concentrate from this ceramic ultrafiltration system is continuously recycled back to the precipitation tank of the multi-flow, and then the filtrate, or permeate as it's sometimes called, from the ceramic UF is neutralized and reused in the shale oil operations as either frac water or injection water, reducing the freshwater demand. So this slide shows some photos of multi-flow package units. We can also provide them as field erected units in any size that's desired. As I mentioned, multi-flow is used for the removal of hardness, metals, silica, and suspended solids, typically operating the pH in the range of 10.5 to 11 for chemical softening. The chemicals are selected on an application-specific basis and can be any combination of lime, soda ash, caustic soda, and sometimes a magnesium additive when we're trying to remove silica. Multi-flow uses lamella modules for high rate settling, enabling a footprint that's 15 times smaller than a conventional process. It uses a patented mixing technology by Veolia called TurboMix, as I'll describe in more detail shortly. And it typically produces a dense sludge in the range of 6 to 10% dry solids. And we generally get a good quality effluent and low hardness. So this shows a more detailed schematic of the multi-flow. The influent water enters in from the left side, and it goes into a coagulant tank where we add a coagulant if it's even necessary. Sometimes it's not. The water then flows into the heart of the process, which is this precipitation tank, where we have the TurboMix mixer. This is where the alkali chemicals are typically injected, lime and or caustic or soda ash, if needed. The precipitation tank, it uses this TurboMix draft tube technology for improved mixing, and we typically maintain a pH of 10.5 to 11 to facilitate chemical softening and silica metals removal. The water then overflows into a flocculation tank and then into a settling tank. The solids settle to the bottom of the settling tank. Most of the solids are recycled back to the precipitation tank, whereas some of the solids are intermittently wasted to the filter press. So this shows the TurboMix technology. So within the precipitation reactors I showed you on the previous slide, this is a proprietary draft tube mixing technology we call TurboMix. It enhances crystal formation while minimizing the retention time, power, and chemicals needed to carry out the precipitation reactions. This reactor provides optimum mixing efficiency and enhances the reaction kinetics with a high level of homogenization. So it minimizes short circuiting and dead zones and enables the reactor to achieve classical precipitation efficiencies within a smaller tank. TurboMix enables the chemical softening reactions to come to completion within the precipitation reactor, essentially eliminating unwanted post-precipitation downstream of the multiflow. You don't want your solids to be coming out after the multiflow. You want them to come out in the reactor so they can be removed in settling, basically. So this is a slide of the ceramic ultrafiltration module. So after we've taken the bulk of the solids out with multiflow softening and settling, the water is then sent to the ceramic ultrafiltration membrane. This is generally use a 0.01 micron membrane. It's generally titanium oxide material construction. It's an inside to outside membrane operated in crossflow. It gives a very high quality effluent. It essentially removes all of the particulate solids and oils, and it serves as an absolute barrier to particulates. So if you have any upsets upstream, particularly in an oil field where you have some oil, high levels of oil coming through occasionally, this will basically remove all of that. And it has excellent thermal and chemical resistance. So we generally get a high quality effluent, essentially very low non-detect and free oil, suspended solids, and very low in bacteria. This is a schematic of the membrane to show how it works. The feed enters in one side and the concentrate out of the other. You can see there's these passageways. They're actually coated with the membrane material. So the membrane rejects the solids, which end up coming out the concentrate end, while the water permeates through or filters through. It becomes the filtrate or permeate, and it ends up coming out these conduits at the end. Although not shown in this diagram, there's actually a boot seal here that isolates the concentrate from the filtrate or permeate, so there's no cross-contamination. So the concentrate comes out this end, while there's, although not shown here, there's a nozzle on the vessel where the filtrate is collected. So this shows how a system is comprised. You have modules, you have the actual membrane inside of a housing. Well, actually, first of all is the membrane element itself, which I showed you on the previous slide, the ceramic ultrafiltration membrane. And that goes inside of a housing to form a module. And those modules are put together to make up a membrane skid. You'll have recirculation pumps, and all the piping that are skid mounted together. And then you might have several of these membrane skids to make up a whole system, along with clean in place facility system as well. So this shows you the typical performance we get out of a ROS system. And you can see some of the photographs here of what the produced water looks like that we're being fed, as well as what the multi-flow effluent looks like, and finally the very pure ceramic ultrafiltration membrane filtrate. So look at the color coding here. We have the PW, MF, CP, and FP designating what we're showing in these photos. So the water coming into the ROS could be very high hardness, anywhere from 100 to 25,000 ppm as calcium carbonate, high in iron, manganese, barium, strontium, oils, and TSS. So the multi-flow chemical softening effluent, which is shown here as MF, removes the hardness down to 100 ppm or less. Depending on the application, we can get even much better than that, like 10 or 20 ppm. It really depends on the application and the temperature of the water. Essentially, we oxidize and take out the iron and manganese, so it essentially takes out all that, and the barium and strontium absorb onto the sludge. And it takes out the vast majority of the oil and the TSS and the multi-flow itself. And then the ceramic ultrafiltration process that permeates essentially removes all the rest of the free oil that made its way through the multi-flow, carried over into the effluent. So it essentially takes out all of the free oil and TSS and bacteria, and you can see that very pure ceramic ultrafiltration permeate. And then finally, all of those solids that were removed from here are in the filter press cake. And typically we get at least 50%, sometimes as high as 80% dry solids content in the filter press in these chemical softening applications. So the benefits of ROS, we're able to run at very high recovery rates. Essentially, the only water we lose is the moisture that's in the sludge and a little bit of clean in place waste, but we get generally greater than 98% recovery of the water. And we're removing all the scale formers and particulates. As I mentioned, the ceramic ultrafilter serves as an absolute barrier to particulates and bacteria and oils, so you don't get any carryover downstream due to upstream upsets. We can accommodate with the ceramic membranes temperatures, up to 210 Fahrenheit, and it's a compact technology by using all those membranes, and then we can stack them on top of each other, as you've seen on that earlier photo. We can reduce our footprint requirements by 30%, and then all this is this technology is available as package treatment systems, which are pre-piped, pre-wired for modular installation, which helps in sites where field installation is expensive. So this is a case study of a design, build, operate project we provided to a confidential oil company in Utah with performance guarantees by Veolia. It's a water flood oil field, and prior to our involvement, it used commingled water as injection water. The commingled water they were using is a blend of produced water and fresh water, and it had high scaling and corrosion tendency. Even though the field was using basic water treatment processes for coarse removal of oil and solids, the commingled water source was unsuitable water quality for their water flooding operation. You can see how this source water scaled and corroded their injection water pipes. This is what their pipes looked like before we got involved in this project. As a result, the oil field suffered from reduced oil recovery from its formation due to low reservoir injectivity rates, plugging of the pores of the formation with inorganic scales and particulates, scaling and corrosion of their pipes and injectors, and also high chemical demand for operation. Thus, these problems were key drivers for the client wanting to change to a ROS system to eliminate the problems and improve oil recovery from the formation. The client contracted us to provide a 20,000 barrel per day ROS system so they could eliminate freshwater usage and treat their oil field produced water for reuse as injection water. Thus, the treatment objectives of the ROS system was to remove scale formers and particulates. In addition, we used a fuel gas deaerator downstream of the ROS system to remove dissolved oxygen to reduce the corrosion potential in the water flood injection water. So you can see from this flow diagram, similar to the previous diagram I showed you of ROS technology, it's a very similar process. One thing I want to note here is that we had to add some sodium hypochlorite for iron oxidation. So as I stated on the previous slide, we also had to add a fuel gas deaerator downstream of ROS to meet the client's dissolved oxygen removal requirement. They needed less than 50 parts per billion oxygen in their injection water. And as you can see in this table here, the water that's very high in free oils, suspended solids, hardness, and bacteria. And as you can see, we easily achieved all of our removal requirements for each of these contaminants, for which we provided performance guarantees. You can also see this photo here of the feed water, the multi-flow effluent, and the ceramic UF permeate. You can see how clear the UF permeate is compared to the feed and the multi-flow effluent water. So this project was a good success, and it saved the client a lot of money in terms of chemical costs and allowed them to get a lot better production out of their oil field reservoir. So now I'm going to shift gears a little bit here and talk about our second generation OPUS technology. Now OPUS involves some extra treatment steps downstream of ROS to basically desalinate the produced water or whatever type of downstream oil and gas water we're treating. So this slide shows you some of the challenges that are typically faced with conventional RO membrane technologies when you're treating challenging water such as produced water or refinery wastewater. You have scaling issues due to sparingly soluble salts like silica and the various calcium salts like calcium carbonate and metals in the water. You have fouling issues due to organics. There's a lot of dissolved hydrocarbons in produced water, and there's also free oil and suspended solids. And then you have salt rejection issues. A lot of the produced waters are high in boron and organics. And if you're going to treat the water for a surface water discharge, you have to meet stringent requirements on removing boron and organics. And then which conventional RO at neutral pH doesn't do a very good job of. And then there's all kind of contaminants in the water that can degrade the RO membranes. And furthermore, all of this is exacerbated by the client's frequent need to have a high recovery system. They want to maximize the amount of water generated and, more importantly, minimize the amount of liquid waste that would require deep well disposal. And running at that higher recovery makes all these issues even more challenging for conventional RO systems. So we looked at the possibility of running an RO at a high pH, and I'm going to show you some slides here that show the benefits of high pH when in conjunction with RO treatment. So silica at neutral pH, it has a very low solubility. This graph shows 100. A lot of times it's as high as 120 ppm. And oftentimes silica is the contaminant that limits the recovery of a reverse osmosis system. However, if you raise the pH, notice when you get above 10, there's a dramatic increase in the silica solubility. And what happens is you're ionizing what is otherwise at neutral pH monosilicic acid, which is a uncharged acid. You're ionizing it into a anion, silicate, at high pH. And that silicate becomes easily rejected by the RO membrane, and it doesn't foul it. So this is one example of how running an RO system at a high pH, above pH 10, helps control silica fouling, which would otherwise reduce or limit the recovery of an RO system. Here we can get well over 800 ppm silica in our RO concentrate. Another example is dissolved oils present in the water, in produced water. At neutral pH, they tend to be present as organic acids, which tend to foul RO membranes. For example, naphthenic acids or phenolic acids. But as you raise the pH up above 10, they start to become more and more soluble, and therefore they ionize. Like, for example, naphthenic acids ionize to naphthenates, which is an anion which is easily rejected by the RO membranes and doesn't foul them, or phenolic acids to phenoxides. So running at high pH helps maintain these dissolved oils in solution so they don't precipitate and foul the RO membranes. And then similarly, hydrogen sulfide, at neutral pH, half of it exists as H2S gas. You can see here the percentage as the gas, and half of it as bisulfide, which is an anion. As we raise the pH above 10, it's essentially none of it exists as an H2S gas. As you know, H2S gas can cause issues. It's a safety issue above certain concentrations. It has adverse health effects and can even kill someone when you get into the hundreds of ppm. And then also it could have air emission issues, and also if not handled properly, H2S can form colloidal sulfur, which can foul RO membranes. So by running the RO system at high pH, we maintain the H2S in its soluble form as bisulfide, thereby eliminating some of the issues I just mentioned, and eliminating fouling issues on the RO membranes. And finally, boron. So at neutral pH, boron exists almost entirely as boric acid. It's an uncharged acid, and it's poorly rejected by RO membranes. Unlike the others, it's not a foulant, but in certain applications, especially if you're discharging and have a discharge permit, you have to meet a tight discharge limit on boron to discharge to a surface water. But by raising the pH, we're ionizing that boric acid to borate, and essentially at the pH range that we operate in the 10 to 11 range, it's almost entirely almost entirely borate as an anion, which gets very well rejected by RO membranes. So all those aspects of high pH are what make OPUS technology, it's basically an elevated PHRO operation effective. So OPUS is an acronym, just like ROS. It stands for Optimized Pretreatment Unique Separation Process. And we developed this technology for high fouling and scaling applications, very dirty waters that have a lot of hydrocarbons in it, like oil and gas field produced water, frac flowback water, and also other challenging waters like cooling tower blowdown waters. So it's designed to treat these very challenging chemistry wastewaters associated with oil and gas industry. And then the product water can be used for surface discharge to a river, process water reuse for, say, steam generator or boiler feed water, as well as beneficial reuse applications like irrigation. So as I mentioned, we're running the RO at an elevated pH, and as I described in those preceding slides, it helps to control organic fouling, silica scaling, and boron by the first two of these keeping them soluble so they don't foul out or precipitate on the RO membrane. In the case of boron, keeping it ionized as an anion, borate, so it's very highly rejected. And then in addition to that, we have optimized pretreatment ahead of the RO membrane. That would be the ROS system, which I previously described, to remove the scale formers and the particulates, oils, solids, and bacteria. So the benefit of the OPUS technology is we're able to achieve high recovery rates with low liquid volumes, and typically we can get greater than 90% recovery on applications where the feed total dissolved solids is less than 7,500 ppm. And this is a Veolia patent technology covered by a couple US patents as indicated here. This shows a schematic of the OPUS, second generation OPUS system. Now, the first part should look familiar to you because that's what I described earlier as the ROS technology with the multi-flow chemical softening and ceramic ultrafiltration. So we take that a step further and treat it with ion exchange softening to remove hardness down to trace levels. Why do we need to do that? Well, because we're going to run the RO at elevated pH, and we need to essentially take out all that hardness, which would, if we didn't take it out, would be a scaling issue when you're running at high pH. But now that we've taken out all the hardness, we're free to run at high pH. We also have a cartridge filter to protect the RO membranes. We had some anti-scalant. And this is essentially the technology where we can, this treated water, we can either send it to surface discharge or reuse it for other applications like boiler feed water. So one of the technologies, as I introduced earlier, is the ion exchange softening. We use a weak acid cation ion exchange system operated in the sodium form, and this can handle high TDSs up to 30,000 ppm or even higher, unlike conventional strong acid cation softeners that are regenerated with brine. There's no pH change across the resin when running in sodium form, so we maintain a high pH the whole way in the OPUS process, coming out of the ROS and through the WAC and the RO. And we regenerate with acid and caustic, and we get a high quality effluent hardness less than 0.2 ppm to feed the high pH RO. And then the RO system, it's for removal of dissolved salts, silica, boron, organics. It just uses a conventional thin film composite spiral wound seawater RO membrane. We generally use a seawater membrane that has 99.8% salt rejection, operating typically in the feed in the range of 10.5 to 10.8 pH. And we can provide these anywhere from 600 to 1200 psi pressure vessel rating with energy recovery options where needed, multi-stage configurations to achieve 85 to 95% recovery rate. So as I mentioned earlier, some of the benefits is for the OPUS technology is once we've removed all the scalants and foulants and or kept them soluble, so really either we're taking things out upstream, like in the ROS system, removing scalants and foulants, oils, scale forming compounds, completely removing from the water prior to the RO, or we're running at high pH to keep those salts like silica, as I mentioned earlier, or certain organics in solution while it's in the ROs. That's really the two things that we have working in this process to maintain fouling and scaling control. And as I mentioned, by the time you've dealt with all that scaling and fouling, the RO system is really only limited at that point by osmotic pressure, not by scalants and foulants. So generally, if the system TDS is less than 7,500, we can recover 90% or higher and get an RO recovery of 92%, because at that point, we're pretty much limited by osmotic pressure. And by using this system with the Ross system, we're able to achieve 30% less space compared to conventional operations, conventional approaches. And then I want to point out that by running in high pH, it's essentially a continuous clean in place process. We've had membranes that we've been running for 2 years and we didn't have to do a CIP just because we're continually cleaning by running at high pH. But generally, it eliminates or makes the CIP very infrequent, like once every 3 months. And then we get high salt rejection of the silica, boron, and TOC due to the leveraging the high pH as I showed you in those previous slides. So now I'm going to talk about a case study. This is where we applied OPUS at a oil field in California. This is a confidential customer. This is a design, build, operate project where we have a 12-year operation and maintenance contract, which we're currently executing, and we do provide performance guarantees on this project. This is an oil field that uses enhanced steam injection or steam flooding for enhanced oil recovery. And there's two phases of this. We're treating half of the water is treated as reuse for steam generation, and the other half of the water is further treated for surface discharge to a pristine California creek. It's a 50,000 barrel per day plant, so roughly half of the water goes to steam generation, half to surface discharge. We're using the OPUS II technology. Previous to us getting involved, the client had issues that they weren't, they kept on recycling the same water, using basic treatment to recycle it for steam generation, and they were getting high formation pressures and reduced oil recovery, and then they were also limited by the amount of liquid waste that they generated from their produced water that they could put back in the ground and deep well inject. So by providing this plant, we were able to allow them to expand their oil production by sending a half of this water to an outlet which they previously could not send to, which is this creek that we're surface discharging. So we're essentially dewatering their reservoir, reducing their injection volumes, and allowing to get greater efficiency in their oil recovery operation. So this is the process that we have. The first part is the OPUS II technology, which I described in the preceding slides. And then we also have some post-treatment that's specific to this project in itself, which Veolia does provide custom engineering on these plants. So we do look at the most optimum approach and look at different options to meet your needs for discharge on the most cost-effective way. So the post-treatment here was put together on a custom basis. So the produced water comes in, and we have the OPUS II process. We have the chemical softening, ceramic ultrafiltration, WAC, and that's where I was telling you half the water roughly goes for reuse to steam generator makeup once through steam generator, and then the other half we have to cool it down at that point. The water is hot. In fact, here's the quality of the water. The other half of it is cooled down and goes on to after it's wax off, and it goes on to double pH, high pH RO, and then on to the post-treatment. Finally goes to surface discharge. As you can see here, the water is hot, 160 to 200 degrees Fahrenheit coming in. It's high in organics, TOC and COD, and hardness and silica, and boron also. And we have to meet some stringent specs. So to go to the steam generator, the once through steam generator, which is this reuse application, we have to basically remove all the free oil, TSS, hardness in conjunction with, we use ion exchange softening to get it down to 0.5, and silica, they went less than 50. So we meet all these needs for the steam generator, and then the other half of the water that's cooled down, we have to meet a very stringent limit on boron, less than 0.5. This is what goes to the creek. And then less than 1 ppb on benzene and phenol. And then ammonia, we actually use ammonia polishing ion exchange. We have to get down to less than 0.025 ppm ammonia in the unionized form. So as I said, this is a 50,000 barrel per day plant, and we had to guarantee the quality here. So this is the results we got going to the steam generator. These were what our specs were that we needed to meet, and we easily met all of our specifications using the Ross technology to remove free oil, suspended solids, hardness, and silica. And then this is the rest of it that's going to the creek, where we're further using high pH RO and the post-treatment that I showed. We're meeting our limits, the stringent limit on boron, less than 0.5. We're getting pretty much non-detect with double pass high pH RO, ammonia, as well as benzene. Now benzene, we're pretty much achieving our limit of less than 1 ppb with the double pass RO itself, but we did on the previous slide have advanced oxidation system, hydrogen peroxide and UV, to ensure we would always meet that limit. Because don't forget, there's a permit here, and Veolia has to guarantee the performance, and so we needed to have an extra safety net to ensure that we never were off spec on benzene, and we have not been in 6 years of operation. So this is the quality we get, and we meet our phenol 1 ppb phenol limit as well. So to summarize, we're achieving our goal of over 90% water recovery on this application, and we have a compact footprint with the use of the ceramic ultrafiltration, reducing the footprint size by 30%. A high quality effluent going to the steam generators. We removed all the oil and solids, reduced maintenance, and it's also effective in fouling and scaling control. We've tested the system when we were piloting, spiking oil levels up to 300 to 1000 ppm, and we didn't have any issues with the ceramic ultrafiltration. And then we were able to guarantee all of our, we've been running for 6 years, and we have 100 constituents that we're regulated on in our discharge permit, many of them to ppb levels, and we've never had one discharge violation yet in 6 years, meeting this very high quality water for surface discharge. So I'm going to go over just one last study here. This is actually our first, it's a recent OPUS installation, our first OPUS installation at a refinery. And before we got involved, the client was treating river water via chemical softening and media filtration and ion exchange softening for use as boiler feed water and cooling tower makeup. They were also treating the refinery wastewater via conventional oil water separation processes followed by activated sludge. And then finally, as I've indicated in blue here, they had to use tertiary treatment using coagulation, flocculation, settling, and sand filtration to achieve selenium removal prior to discharging this refinery wastewater to a river. However, the client was wanting the flexibility to use a different crude oil feedstock that had a higher selenium content. And being that selenium was regulated in the discharge permit, I believe it was 60 ppb or something like that, and selenium treatment is expensive, the client decided they wanted to stop treating their refinery wastewater for discharge, and they decided they wanted to do the following. They wanted to get rid of this tertiary refinery wastewater treatment to remove selenium, and they wanted to eliminate all their discharge to the river. Instead, what they did was they sent the refinery wastewater secondary effluent after the activated sludge to an OPUS system that we provided. And then this OPUS system would provide the boiler feed water and cooling tower makeup, would basically reuse that water produced by the OPUS system for boiler feed water and cooling tower makeup, thereby reducing the amount of river water consumption that the plant would have. So this slide shows our design basis of this OPUS system treating this refinery wastewater secondary effluent. As you can see here, the water is very high in hardness, silica, and COD, which would likely cause problems with scaling and fouling in a conventional neutral pH RO system. And you can see the requirements here for boiler feed water, including TDS of less than 150 ppm. There's also a requirement for our RO concentrate to have a hardness of less than 5 ppm. Furthermore, we needed to provide 2,000 GPM of boiler feed water capacity and run the RO at 92% recovery or greater, such that the RO concentrate to the deep well injection would not exceed 200 GPM. And we also provided performance guarantees on complying with this entire design basis. So this is the treatment process. The client was actually had existing, so this is the OPUS technology in this red box. The client actually had existing solids contact clarification and a compressible media filter that was existing. So that was outside of our scope. Our scope really started at the WAC ion exchange softening and the high pH RO. And you can see that the skid, the RO skid we provided. And this is actually a semi-batch mode operation RO using a single stage. So we're operating in a semi-batch mode. And you can see a rendering of the of what the skid looked like. We weren't allowed to take pictures on site here, so that's why we took this picture before it got to the site. And we were producing boiler feed water, and some of the water the client took off before the RO system to send to a customer of theirs to send soft water after it had been softened with ion exchange. So that's the treatment process that we used. And the initial process that the client wanted before we convinced them to use OPUS was using an alternative process that was using a Fenton's reagent for oxidation of organics and granular activated carbon filters and two-stage neutral pH RO to deal with remove the organics via Fenton's reagent and GAC, and finally run at neutral pH RO. The difference with our OPUS process is that we're using the WAC ion exchange softening, and we use a single stage high pH semi-batch mode RO to avoid scaling and fouling while running at 92% recovery. So we figured we saved a tremendous amount of GAC as well as steam and chemicals, resulting in 65% savings in OPEX compared to the client's original approach. So this plant is not yet fully commissioned. We have 3 months of successful operation treating the refinery wastewater and achieving our requirements for production, effluent quality, and recovery. However, the existing compressible media filters that our client provided are not providing the needed performance requirements for fine particulate solids removal, and we're getting some submicron particles that are getting trapped in the RO. Our client has acknowledged that there is a problem with their compressible media filters, and they're currently working with us to evaluate finer filtration options, such as using ultrafiltration. So that's that case study. And furthermore, finally, I want to just add that Veolia offers piloting services, especially for applications involving challenging produced water treatment chemistry and stringent requirements for treated water quality or high recovery. Some of the key goals of conducting piloting is to validate the system performance, confirm long-term treatment costs, and expose process risks or unforeseen challenges prior to building a full-scale commercial system. We can offer services for 24/7 operation of ROS or OPUS systems, and although a longer duration may be needed depending on the application, we recommend a minimum of 6 weeks of continuous operation for piloting, which equates to a minimum of 10 weeks on site, including the mobilization, shakedown, and demobilization. So in summary, ROS, OPUS, and OPUS II are viable solutions for treatment of produced water and refinery wastewater, as we've demonstrated in the case studies I presented at the Utah, California, and Midwest refinery sites. The product water is highly suitable for produced water and refinery applications involving treatment for reuse, surface discharge, or for boiler feed water, and also for minimizing waste generation. We generate a high quality water suitable for irrigation, for low boron, TDS, and organics concentration. We can run these technologies, OPUS and OPUS II, as high as 30,000 TDS, but generally around 7,500 ppm TDS or less gives you the best fit for 90% recovery or higher. We have multiple installations of produced water treatment and years of operation experience, and we most importantly can offer process guarantees on the process performance. We guarantee the performance of our systems, and we have capabilities to do piloting to demonstrate and confirm the treatment costs, and the capacities can range anywhere on a full-scale plant from 5,000 barrels per day up to 500,000 barrels per day. So that's the presentation. Here's my contact information if anybody has any questions afterwards, and at this point we can entertain any questions.
Um, thank you, John. That was great. Thank you for the presentation. Before I give you these questions, I just want to remind everyone a survey is going to pop up as soon as this webinar is over. Just 3 questions. It'll take you a minute, and if you would fill it out, it'll let us know how we did today. Just want to remind everyone, if you were interested in OPUS II, that there's a handout embedded in the webinar, so feel free to print that out. A few people have asked, will they receive handouts of the slides or a recorded webinar? The answer is yes. You will receive the recorded webinar in your email inbox at 1 p.m. Eastern Time tomorrow. So look for an email from Veolia Water Technologies. With that, sometimes those end up in spam folders. So if it's 1:15 tomorrow and you don't have it, you might want to try there first. And we have a lot of questions, lots of questions. So I apologize in advance if we do not get to yours. Um, First one here, what membrane life do you typically get from the ceramic ultrafiltration membranes?
Yes, generally 3 to 5 years, but we've had at the one California site, we've been running that plant for 6 years, and I think half the membranes have been running for the full 6 years without needing replacement yet. So, it can range 3 to 6+ years, really.
Okay. Uh, Here's another one. What type of polymer do you use in multiflow?
Well, for ROS applications, we found that we generally don't need to use polymer. We can actually, being that we have the multiflow effluent is going to be further treated by the ceramic ultrafiltration, we find that it's actually good to have a little bit of solids in the carryover feeding the ceramic ultrafilter. It can easily handle that in cross-flow mode. So generally, when running multi-flow in a ROS application, we don't use polymer. In a general application, if we didn't use ROS, we would consider using some anionic polymer. But in ROS, we find that polymer is generally not needed in the multi-flow.
Okay. What are the temperature limits for the RO membranes?
Well, the Aura membranes we use in Opus, they're nothing special about them. They're just standard thin film composite seawater RO membranes. And the limit is generally, I think the warranty limit is 113 Fahrenheit, which is 45 Celsius. We generally run them as high as 40 Celsius or 105 Fahrenheit. As you may have seen on that slide that I showed of the California installation, we use a heat exchanger to regulate the temperature to around 38 or 40 degrees Celsius. The hotter the temperature, you enjoy lower pressure, but the hotter the temperature, you also get higher salt passage. So there's a balance there.
Okay. Here's the one that came in a little bit ago. Can you comment on the upper limits of chemical constituents and impurities that the ROS system can handle? And that's namely the upper limits of barium and strontium, which are elevated in the Marcellus.
Yeah, I find that the effluent that you get, it's more limited by, it's more a function of the solubility. We have had some higher levels of barium. In fact, let me go back to, I think, one of the previous slides. We showed some ranges that we've seen. Let me go back here on barium and strontium for the ROS applications. Where was I? Here we go. We've seen up to 1,000 ppm in Marcellus applications of barium and strontium. It tends to adhere to the sludge. It's more of an absorption onto the solids, and generally, the solubility is pretty low. That we're able to achieve barium less than 2 and strontium less than 10 just by chemical softening itself with the right amount of sludge recirculation, leveraging the fact that at the high solids concentration of the solids that we're recycling, the barium and strontium tend to absorb onto the solids.
Okay. What's the TDS max the ROS system can treat?
There's really no TDS max on Ross. The TDS is more applicable to the Opus once you get to having to desalinate with an RO membrane in high pH mode. Uh, Marcellus produced waters can have very high TDS. So it comes, we talking up in the, I believe in the 200,000 ppm TDS range. It gets pretty high. The biggest thing there gets to be corrosion issues and materials selection. Of course, with that being said, high TDS does tend to slow down kinetics of chemical softening. So when you're getting to those higher TDS waters, one thing we do like to do at the very least jar testing and preferably some pilot testing. Jar testing is very helpful just to reveal the kinetics. As I mentioned, at high TDS, the reactions tend to occur a little more slowly, and so you need enough reaction time for that. But really, we could treat up to those very high TDS concentrations. It's just making sure we have the right materials of construction to deal with potential corrosion issues due to chlorides and due to the slower reaction rates at the higher TDSs that you might find in like a Marcellus shale produced water.
Okay. What is the recirculation flow percentage around the ceramic ultrafiltration system?
Yeah, it tends to be a very high cross flow rate, and it really depends on the application. It could depend on the temperature, the amount of oils you have, the free oils you have in the water, but it could range anywhere from probably 3 times to 10 times the incoming flow to maintain the right cross-sectional velocity. You want to have enough turbulence in there to discourage adherence or fouling of oils and solids to the membranes itself. So it does use a pretty healthy cross flow.
Okay, thank you. Here's another one. How much is the maximum allowable oil as ceramic filter feed water?
Yeah, we've, as I showed in an earlier slide, we did a pilot study where we were spiking the water. We were just trying to see where we would, it's like more of a stress test on how much oil we could put into the ceramic ultrafilter before it fouled up. And we actually went as high as 1,000 ppm. And we were doing this for a week straight, and it didn't seem to adversely affect it. Uh, Generally, yeah, but we could accommodate hundreds to 1,000 ppm, and a lot of it. Keep in mind, a lot of that oil, we're not using the ceramic ultrafilter as the first step in our process. We do have the chemical softening, and a lot of that oil will absorb onto the sludge itself. Uh, in some applications, we might consider adding some upfront oil separations technologies, but generally we could accommodate hundreds of ppm feeding the raw system before we would start to consider using upstream, things like dissolved air flotation or walnut shells. Generally, we could do up to a couple hundred ppm and not need that and handle it directly with the raw system.
Okay. All right, thank you, John. We still have more questions, and I apologize if we didn't get to them. We're going to go ahead and cut it off now. We've gone a few minutes over time, but if you have more questions, here's John's email. Feel free to reach out to him directly. Thank you, everyone, for dialing in today and attending our webinar. Have a great day.
Thank you.